Hello everyone, my name is Zeyu. Glad to be here. So today I'm going to talk about our work, PerfOMR Oblivious Message Retrieval with reduced communication and computation. It's a joint work with my wonderful collaborators, Eran, Tromer, and Yunhao, Wang. So let's begin with motivation. Anonymous message delivery system. So in the system, there's a sender and a recipient. The sender wants to send some message, send some payload like a text message or coin transfer to the recipient. What it does is that it first puts the payload on some bulletin board, and this bulletin board is essentially the central database in messaging apps like Signal or WhatsApp, or the public ledger in the case of a cryptocurrency like a Zcash or Monero. And then the recipient tries to find the messages that are pertinent to them from this bulletin board. There have been lots of work studying about bulletin board privacy, sender privacy. The question is, how about recipient privacy? How can the recipient retrieve the messages that are addressed to them without leaking identity or metadata? So a naive solution is just simply to let the recipient download the whole bulletin board and locally filter out the messages that are addressed to them. But this can be too expensive in terms of both bandwidth and computation. So what we want to do is we want to outsource this job to some untrusted third party, which we call a detector. Let's take a more detailed look at the model that's used in our work and many other works. And also the model is building from the model from FMD. So as promised, there's a sender, a recipient, and a board. The recipient uses its secret keys to generate some public keys. The sender will use the clue key, which is public, to generate some clue. And the clue is concatenated with the payload and then put on the bulletin board. The detector will stream the entire board and then use the detection key from the recipient to generate some digest, send back to the recipient. The recipient will use some secret keys to decrypt and get the plaintext payloads. And this plaintext payload should contain all the pertinent messages addressed to this recipient. So property-wise, for security, we want the detector to learn nothing about the recipient. It should not learn which messages are pertinent, which messages are not, and it also should not learn who is doing the retrieval with what keys. Efficiency-wise, we want the digest size to be much smaller than the bulletin board size. Essentially, or ideally, it should only be proportional to the number of pertinent messages. So there are two main technical difficulties in this primitive. The first is that how can we obliviously find the messages that are pertinent to a recipient? And the second is how can we obliviously compress all the pertinent messages into a small digest? And in this paper, we introduced techniques to address both of these problems more efficiently than prior works. So let's first recall how it was done in LT22, the original OMR paper. So essentially what they do is that the sender uses some public key encryption to encrypt L bits. And then this ciphertext is used as a clue to put on the bulletin board. And then the detector will use homomorphic encryption, FHE, to homomorphically decrypt all this L ciphertext and get a bunch of ones. So if the message is pertinent, then because the key used are identical, it should get ones. And then with an AND gate, it will get a single one, indicating the pertinency. And then for the impertinent messages, after homomorphically decrypt, it will get 0 or 1 with probability half. And then with an AND gate, you will get 0 with high probability. After getting all these M bits for M messages, you obtain a pertinency vector. And this vector, if the recipient can see this vector, it will find out which messages are pertinent to them, which are indicated by 1, and which messages are impertinent to them, which are indicated by 0. And in LT22, how they instantiate this PKE and FHE is that they use PVW and BFV. So let's first quickly recall what those are, and it will be also helpful for our techniques. So PVW is a public key encryption scheme that's lattice-based. They work over ZT for some prime T. Technically, it doesn't have to be prime T, but for the case of our talk, assume T is prime. And then the ciphertext format are essentially just two vectors, ZT vectors. The first is the A part that has length A for some length n for some security parameter n. And then the second vector is B that has length L to encrypt L bits. And then there are a bunch of secret keys. The secret keys are essentially L ZT vectors, and each of which has length n. So the decryption process is the only thing we care about in this talk, so I'll only recall this part. The decryption is essentially just the inner product between the A part and the ciphertext and each of the individual secret keys. And then the result is added to the each B part, and then we will perform a range check to the result. If the result is within the range negative beta to beta, we'll return 0, otherwise we'll return 1. And this beta is some error parameter, which we'll discuss in a bit more detail later. But after this process, we'll get a bunch of zeros or ones, and these are just the alphabets that we need for decryption. So for BFE, BFE is essentially just a homomorphic encryption scheme, and it supports the packed SIMD field elements. What it means that it operates over ZT, but it works over a vector instead of just a single element. So for example, for addition, if you have two BFE ciphertexts encrypting two vectors, V and W, after you add them, you will get the resulting ciphertext that's encrypting the V plus W element-wisely. And then for multiplication, similarly, you will get a encryption of V times W element-wisely. Okay. And then what LT22 does is that it uses PVW and BFE to realize the PKE and the FHE part respectively. So this is what prior work does. And then our very first observation is that we can just change PVW that's using LWE to using ReLWE. Okay. ReLWE is the PK scheme that based on ideal lattices, so it has a lot of better properties, which we'll discuss in a bit. And it shares a similar ciphertext format and decryption process as PVW, so we don't need to recall them again. And but it is much more efficient, which we'll cover in a sec. So our first step is just changing PVW to ReLWE, and the sender will just use ReLWE to encrypt a bunch of ones, and then the detector will homomorphically decrypt all these ReLWE ciphertexts for now similar process. And the first advantage is that it now has a much smaller public key size, so the clue size will be much smaller. But more importantly, it will have faster decryption if we want to perform it homomorphically using the technique that I will describe in the very next slide. So our second technique is that we want to use a different range check function. Let's first recall what's the decryption process. It's first the inner product and followed by a range check. If we want to do it homomorphically, the inner product part, B minus ASK, is very easy under BFE because it's linear operation. But the range check is much more complicated because it's not natively supported. So what LT22 does is for the range check, they will interpolate a degree T minus 1 polynomial, which requires essentially OT BFE multiplications, thus can be very slow. So what we propose in our work is that we propose a different circuit that requires only 2 beta plus log T multiplications, and this beta is the error parameter that I just mentioned. So our circuit works as follows. So we first compute y equals to the product of x minus 1, where I is in negative beta to beta, so the entire error range. If the input x is within this range, the resulting y will be a 0. Otherwise, it will be a non-zero element. And then we raise y to t minus 1, recall t is a prime. And in this case, y will be 0. If y is 0, the result will be 0. Otherwise, it will be 1. This will be exactly what we want for the range check function. So the point of using ReLWE is that using ReLWE, we can reduce the error parameter range, error range parameter beta to be omega log t smaller than using PVW. Concretely, it will be like more than 60x smaller. So in this case, our range check will be very, very efficient compared to priors. So this finished the first problem. How can we efficiently find the messages that are pertinent to them? And for the second problem, how can we solve how can we homomorphically encode the resulting pertinence vector, which you recall is the 0, 1 that has basically n bits, into a much smaller digest efficiently. So what LT22 does is that it encodes n messages into a small amount of buckets, as shown illustrated in the figure. So our first observation is that we can just bundle G messages together and encode them into buckets. So instead of n messages, we just add each G of them together, bundle them together, and then hash them to some buckets. And this means that we only need the n over g operations instead of n operations, so it will be much more faster. However, the problem is that now the encoding scheme in L222 doesn't work anymore because the bundled message has more complexity. So what we need is that we need to devise new homomorphic encoding techniques. Due to the time constraint, I will not be able to talk about how we do that. But to summarize, our scheme follows the same paradigm as what's in LT22, but we use first we use ring LWE as a PKE, and then we devise a more efficient homomorphic ring LWE decryption process and homomorphic encoding process to make the entire process much faster. So let's take a quick look at the overall improvement and benchmarks. So compared to OMR P2, which was introduced in LT22, we introduced two constructions, the PerfOMR 1, which is essentially what we've just talked, which is focusing on the detector runtime and using the range check function that I just described. And we have a second constructions, PerfOMR 2. It's focused on clue key and clue sizes. And it requires a new technique, a new range check function we don't have time to discuss. And for PerfOMR 1, as you can see, for both homomorphic decryption and homomorphic encoding, it's roughly, say, 15 to 20 times faster than OMR P2. So resulting runtime is roughly 15 times faster. And for PerfOMR 2, the runtime is still 2 to 3 times faster. But more importantly, for clue key sizes and clue sizes, it is much smaller than OMR P2. Okay. So that's pretty much for today's talk. There are, as mentioned, some additional techniques that I didn't have time to cover in the talk. Some are mentioned, some are not. And with our improvements now, Oblivious Message Retrieval is much more practical. It requires only about $1 per month per recipient for a Bitcoin scale application using our technique. And there have been lots of interesting recent follow-ups. For example, for provable denial of service resistance, asymptotically it's achieved in BT23. Practically it's achieved in LSTW24. And there's also a two-server OMR construction in JMK24. For those who are interested, please check the links. And that's it for the talk. Thank you.